Okay, so what I'm going to do today is, as you can see on the screen, is another unsupervised, which is dimension reductions. Like you remember that we start with the supervised learnings, and for supervised learnings, we should have the data set which has input and the corresponding output or corresponding labels. On the other hand, for unsupervised learnings, we do have only inputs. We don't have any associated labels or outputs. For the first thing that we learn for unsupervised learning is clustering. So I already explained what the meaning of clustering is, and one of the famous one or the most useful one for clustering is k-means. So I think I believe that I cover all the details related to k-means and clusterings. And the second topic in unsupervised learning is dimension reductions. So again, there are many ways or many methods or algorithms under the dimension reduction topics. But the most famous one, or the most often used one, is PCA. It's a principal component analysis. So personally, I believe that it's really important whenever you gather or receive some kind of any kind of measures data or whatever. I think the first step is you have to plot them, or you have to visualize something in order to get some insight or overview of what kind of data that you have. And the second step is you have to do dimension reductions. You have to do dimension reductions. Okay. Because I never explained what the dimension reduction is, but at least I think you can, from the name, or you guys can kind of guess what the physical meaning of or dimension reductions. I'm going to explain it, the dimension reductions, especially for principal component analysis, one by one. So dimension reduction motivations. You don't know what kind of data set that you're gonna receive, and you're gonna be asked to analyze them. And assume that you have, you have 10 sensors in your system. Then probably and suppose that you have 10 sensors and you're gonna get all the data set. So we don't know what kind of time, but this in times instance, you can have 10,000 or I don't know, million data points, and you're gonna receive, this is gonna be the data set that you're gonna have. In this case, I'm gonna say the dimension, 10-dimensional space, right? And on top of this, probably this one is some kind of combination of these from 1 to 10, or this one is probably I don't know, any kind of, you can make another inputs or another features based on this data set. Or another example is this one is probably this could be another inputs, another vectors, right? But as you can see, the data or data set that you're gonna have is will get complicated, or I would say data might be in high dimensional space. Okay. The issue or the problem is that if you have high dimensional data set, we, like humans, it's not easy to understand or get some kind of insight right? So the question or the motivation for dimension reduction is there any way we can describe high dimensional data set in a simpler way, or in low dimensional space, I would say. Okay, that's the motivations. I would say simple is better always, or probably I would say low dimensional data set is always better than this one. But there are some constraints on it. What is that? We want to do dimension reductions because it's okay to believe that this dimension reduction is always good. But there are some conditions. We're going to reduce something, right, without losing too much information. That's the key. That's the key. Okay. So probably say in general, the data set that you might face too is that like in high dimensional data set or in high dimensional space, but we believe that it's a low dimensional data set or simpler representation is better. So we want to conduct the dimension reductions, which is good. But thing is that we want to do dimension reductions without losing too much information. That's the key. Find a low dimensional yet useful representation of the data. Useful representation means same as without losing too much information, right? So I think it's enough as a motivation. So I guess at this moment you guys are convinced that you should do dimension reductions and you should know how to do dimension reductions. So why dimensionality reductions? So so it's into low dimensional structures in a data set. Like I said, the highest dimension that we can visualize is 3. Okay. So in visualization purpose, we have to do dimension reductions, and then we can get some insight on it. And fewer dimensions, that means less chance of overfittings. You guys remember when we talk about the regression problems, I mentioned so many times the overfitting problems and regularizations. At that, when you talk about the regularizations, one of the best ways that build up the simplest model. If your model, the model that you're going to assume is if that's too expressive, you're going to have high chance to get overfitting problems. Okay, why is that? Because you want to do better generalizations. So two purposes, you can get insight on your data set, and you have high chance to get better generalizations if you conduct dimension reductions, and then you represent your data set in low dimensional space. And I guess that's good enough. And another reason that why dimension reduction is so important is that, of course, it's going to speed up the computations. I mean, I don't need to explain more. And less storage requirement. So same as data compressions. Going back to here, instead of having 10-dimensional space, assume that you don't need these. Assume that if say that you did that, the feature selections, and it turns out that these two carries the most important informations, then instead of having 10 columns, you're going to have only 2 columns. speed up the computations and less storage requirement. I guess these two probably is obvious. So there are many benefits, advantage over high dimensional data set. So again, there are many advantages or there are benefits. So I would say like dimension reduction is always good, always good. All right. And side note, dimension reduction is different from feature selection. What's the feature selection? Feature selection is, suppose you have like you have 5 features. Here I'm going to use like features and the inputs and this kind of the vague, so I'm going to mix them. But here I will say features, and remember like the lasso or sparsity and for regressions, and you can do the same things for classification as well, but just I'm going to use the regression examples to explain the concept of feature selections. And say these 2 are key features, and I'm going to neglect or remove or get rid of them. That's a feature selection. Dimension reduction is a different. And dimension reduction is more like feature extraction. So here, just remember feature selection and feature extractions. Right? At this moment, probably you're not going to have clear understanding of these two differences on these 2 terminologies, but I will guess later on, especially when you talk about the PCA, you're going to get clear understanding of what feature extraction is. But you already know the feature selection is, okay? You're going to select some of the features and you're going to throw away rest of them. And feature selection, feature extraction is constructing small set of new features from the original features. You're going to construct, for example, like you have 5 features. Say you have only 2 features after dimension reductions or after feature extractions, and the first new feature is like same as x of 1, and second feature is like, how do I say, I don't know, it could be anything. Okay, so as you can see here, feature selection is part of feature extractions. Like feature extraction has like broader meaning of, and it could be here, I just intentionally add this one is like in order to show that there could be nonlinear mappings, and it could be linear combination as well, like that. Then with the original features, after doing linear combinations, we get another feature, another new features, which is good, totally fine. But we can do like any kind of nonlinear mapping or functions is totally fine. Let's move on. Now I want to reduce number of features. That's eventually what we want to do for dimension reductions or feature extractions. So with that keep that in your mind. Let's see. I think last time I mentioned in the statistics was I mentioned like correlations and covariance matrix and correlation coefficient, things like that. I mentioned a lot. So let's see how those concepts are related to on how can we utilize those concepts in dimension reductions. And highly correlated data set, for example. So let me ask Suppose we have only two. Here is R1 and R2. And we collect them data set. In order to see what kind of data set we have, the first thing is, visualize them to see, get some insight. So that's what I did. And I plot them, and R1 and R2, again, R1 and R2, and R1 and R2. Suppose we get these three different cases. And let me ask, which one, first and second and third, which data set or which the case that two random variables are highly correlated? Which one? Which one is highly correlated? Number one or number two or number three? Right, of course. So let's think about the meaning of correlated data set. Means that if we know R1, then we can get, or we can kind of estimate vice versa, which means that R1 and R2, we have two variables. It's one of them are redundant. One of them is redundant. Then you can see that if the data set, if you find out that some of them are highly correlated, that means we have high chance to get rid of some of them. That means we're gonna have high chance to conduct dimension reductions. That's the key idea. That's the key idea of dimension reduction. Okay. On the other hand, if you plot them, in this case, you cannot conduct dimension reductions at all, because R1 and R2, I will say those two they have nothing to do each other. If I get rid of one of them, that means we're gonna lose a lot of information. We're gonna lose a lot of information. So we have to keep both of them. Okay. So that's key idea from the. Let's move on to now. Let's see the principal component analysis, which I'm gonna say PCA. PCA is so important. So important. Principal component. What was the side note? Don't write it spell like. All right. Principal component. And in order to explain what the PCA is, let's think about the situation or example like that. I mean, suppose you have only two features, suppose, then x of 1 and x of 2, right? And we plot them, we will get this kind of data distributions. Okay, so let's ignore feature 2, for example. Then each two-dimensional example of x now becomes one-dimensional, just like that. Which means that, say, x of 1 and x of 2. Suppose your data is here. That means if you just ignore, that means your data set is located right there. And suppose you have like that. Like basically by ignoring the second feature is that basically same as that you just make projections on everything into x-axis or x of 1 axis. That's what we did. All right. Then your data is just located on top of the x over 1 axis. Then let me ask, what kind of information that you're gonna lose, or you're gonna lose? Probably I would say, or you're gonna say this, right? We're gonna lose. But in this case, are we gonna lose a lot of information by throwing x over 2 away? No, because these are the amount of information that we're gonna lose when you decide to do this dimension reduction or PCA. So I guess this one is high chance to can do PCA. So the answer is no. Most of the data is spread along the x of 1. This is important. In other words, if I can say this one in statistic, in a sense of in a field of statistics, we're gonna say the original data set that we have along the x of 1 axis have high variance, as opposed to in x of 2 axis is very little variance. So another insight or another hint that you can get is that, right? So we again, is the how much information that we're gonna lose or how much information that we're gonna keep. That's really important. And the measure or index or metric is related to variance along that axis. Does it make sense? Okay, so with that, let's move on to another example that we have. Suppose you collect the data set again, it's in 2-dimensional space. And we decide to, okay, so like I said, that you suppose you heard from someone that is a dimension reduction is always good. So you're gonna ignore again in the second features. And somehow you decide to ignore the second features with this kind of original data set with this kind of distributions. Okay, then what we're gonna do. So what's going to happen is that suppose you have data set like that, then again, I'm gonna make projections. So instead of have data set, you will have data set like that. I mean, like in this axis. Okay. Then the same question that I'm going to ask, you're gonna lose much information by throwing away x of 2? The answer is yes, because you're gonna lose a lot. You're gonna lose a lot. In other words, data has substantial variance along the both features.
Sorry, but we know that x1 is equal to x2, right?
Say that again.
We can maybe say that x1 is equal to x2.
1 is equal to x. Oh, in this case.
Yeah.
Okay, so okay. You said probably this is like, right?
Yeah.
So okay, I think you made a good point, but I have that I have answer for that in the following slide. Okay. So in this case, okay. So the idea, actually the idea behind these two examples is that here in the data distributions are pretty much the same. The only difference is it's tilted. But like I discussed, is this one is okay to do dimension reductions, but here I would say it's not okay to dimension reductions, and we have to think why. What makes them different? Okay, so the answer is that, like I said, is in this slide that you have. The idea is that now consider a change of axis, consider coordinate transformations or coordinate rotations like that. So I guess the original data set that you have like that, like x2 and x of 1. In like we saw that in the previous slide, is that in the original data set, it's not proper and it's not okay to dimension reductions or get rid of one of the features. But in new coordinates, and the way that is you guys supposed to is like look at that way, okay? Then this one is actually same as this guy. The only difference is a U2 and U1. Now it's okay to ignore the second features in new axis, in new coordinates. Okay. So with this demo or examples, I think the two messages or lessons that we have to learn is that the first thing is that whenever you have the data set, the first thing you have to check the correlations. Okay, you have to check the correlations. And the second thing is you have to check the coordinates. Like said that this data set and this one, it has the same correlation coefficient. The only difference, they have different coordinates. So two things are related. So you have to consider both of them before you decide the dimension reductions. That's the message with. So in this case, we can do dimension reductions, but the only difference that we have to do projections in that way. I'm pretty sure that you guys get the ideas at this moment. So then the question is that, how do you find such coordinate? How do you find? Let's see. So data is a projection onto unit vector, because it's an axis, so you don't have to worry about the length. So when I say assume that it's unit, so what I mean by unit is that like unit length, we have to find this guy. Then after that, we're gonna make projections onto that. And that's, so in these figures, in the blue is original data set. And the red is dimension reductions data set onto U of 1 axis. Guys, okay with that?
Yes.
Then all the questions that you have to answer is that we have to find U of 1. You have to find U of 1. What's the condition or criteria or objective? Okay, so in this, let me see, in this data set, probably this is gonna be new candidate of a new axis, and that way all kind of coordinates, but you have to pick one of them. We have to pick best. That means it's optimization problem. It's optimization problem. And remember, like 3 key components in the optimization problems. The first thing is what kind of objective function that we're gonna have, we're gonna set or define. In this case, this is gonna be the decision variable or decision vector, right? And we're gonna make projections, and these are the amount of the information that we're gonna lose. So I have to minimize them. Okay, that's the we will minimize. Or second, another way that we can say equivalently, and so this is the data set that we want to make projections, and along u-axis we have to maximize the variance. We have to make them very spread out to have highest variance. Does it make sense? And I will say along u of 2, I want to minimize the variance. That means I want to minimize the amount of information that we're going to lose after dimensional reductions or after projections. And the second way that we can think of is I want to maximize some along the u of 1 axis. I want to maximize the variance. That's going to be the objective functions for PCA. Does it make sense? Okay. And I'm going to find u of 1 using this way. Once we do that, I'm going to show you that these two are equivalent. Basically, it's going to say the same thing. All right, let's move on to, so, and the name is principal component analysis, and I will say u of 1 is a principal component. It's like, yeah, it's principal, it is principal component. So it is a direction of u is maximizing the variability or variance in the data set. So roughly speaking, PCA does change of axis or change of coordinates that can represent the data in a succinct manner, or I would say in a simple manner. Okay, so let me move on to, so again, it's a kind of, we have to find u of 1 and u of 2. So I'm gonna just rotate it, and this animation is really, I think it's useful, and it's gonna help us a lot to visually or conceptually understand the PCA. So while it's rotating, we may make projections on it and see all the red dots and how much is spread out or how narrow it is. And I guess, right, at this moment is the best because the red is the variance. Okay. So this is the good, I guess is the best animation that you can, whenever you think about, or when it comes to PCA, this is the best one that you can. So like I said, how we're gonna do, and same as, so how can you find the objective functions to find principal component in PCA, on that principal component analysis, is that I want to maximize the variance, or I want to minimize the errors, which is the information that we're going to lose. Same as minimize the sum of the squared. And minimize the squared errors, and maximizing variance. In other words, you want to make them more separable. Good. Now let's formalize that with. So suppose we have given data set like that, and let me see. We have with this notation we have n dimensions. Okay, then x we have m data points, which means that with this one is that, so I will say this one is x is, I will say small x is here x1, I will say, let me see, here x1, x2, xn. You see I have xn sensors and I did transpose it. So big X is that x1, x2, xn. And this is first and in next time instant, maybe we will be second data set. How many data set? We have m data set. So these are big, skinny X matrix. It's going to be skinny. Okay. And first thing first, we're going to shift it. So we're going to make we're going to make zero means. So each column compute sample mean and just subtract them. So it's eventually you have zero means. And the second thing is rescaling, which means that we can compute the variance for each column, sigma, and divide by that to make univariance. And like he said that the second step is rescaling is optional. It's okay to do or it's not, it's okay not to do. So it's optional. It really depends on the problems or applications. Sometimes the variance carries the key, like really key information as well. But so in that case, I recommend not to do scaling. But again, before we conduct the PCA, and you have to do the shift to zero means and rescaling, you can easily do that. We're using the sample mean or sample covariance or sample variance. And again, the thing that I want to mention is that eventually you have to do PC. You have to write a programming for PCA, and just remember the shape, because always you have to think about the dimensions, and like you have 10 columns, and each time instant you're going to measure the data points. As you can keep collecting more data set, your X matrix is gonna be skinny matrix. And imagine that if you have you have to have a clear understanding or settings for your shape or your dimensions or your structure of your vector or your vectors or matrix. Now, so I want to compute the variance and maximize them, right? So remember that calculate the variance first, and because remember U of 1, having different U of 1, we will get different variance, and I want to maximize them. And I want to find the U of 1 at such that I want to maximize the variance and to find this guy. So find the unit vector such that maximize the variance of projections. I guess this is the objective functions or optimization problem that you have to define it. Okay, remember that this is the decision variables, And this is the objective functions. And another side note at this moment is that you guys remember when I talk about the statistics and the parameters and statistics and populations and samples, things like that. At that time, I said it's a sample covariance or sample mean, or for the sample covariance. Remember, this is correct way when you divide it, things like that. But for in general, it's for large or big data set, these two, I mean, does not make big difference. So it's okay to use m instead of m-1. That's side note. And let's compute the variance of projected data set. And remember, let's say this x data points and ith data points. It's gonna be u unit. We say u is unit vector. And the projected, I'm gonna make projections here, and this is the length. And another data points, we will make projections. I'm gonna make this, and I want to make these the variance. I want to maximize them. So since this is unit vectors, suppose this is, and if you do U transpose X, it's inner product. Inner product. You remember you give us this, and because U is unit vector, same as okay. I mean, remember, like this is U and X and cosine theta. And this is theta. Okay, use that one and give us this. And right here we have m data points. And since I made everything 0 means, actually you have to do that way, and you have to take like say like that in order to compute the variance. But since we set it, this is zeros, that means we don't need to consider them. That's why we have that one. It's a variance. And next step is, again, it's U transpose X, same as X transpose U. So that's what I did. Okay. And squared, and here, remember, like Y transpose Y same as Y squared. So that's what I did at this one. Transpose this one. Okay. And here we can do that one, and we have to swap it. So U transpose X ith, and transpose is itself, and X ith transpose U, and we do that. And U is just U, has nothing to do with the summation from I to M. So we can take this guy out. So we can do that. So this is the variance of projected data points. And here is the key moment. What is this? What is this? What is that? Remember xi is like column vector, like here, and transpose is transpositive. So it's gonna make M by M matrix. No. I'm sorry. It's a n by n matrix because we have n and n. That's the dimensions. An n by n matrix. And each element and you have to remember, you have to imagine that we have n by n matrix and to take the mean of that. And probably if like, I think like some we might not like is not able to see, but this is same as sample covariance matrix. It turns out it's a sample covariance matrix. It's a sample covariance matrix. I mean, I guess some we might not like, it's not clear from here to that, but please take some moment and think about it like right now or like after this class at home to make sure you understand why this is the same as the sample covariance matrix. Okay. Now we can put everything together and make beautiful optimization forms. That's that. So again, this is like in the previous one, it's a variance of projected data set. What's the constraint? We assume that starting from unit vectors. So this is the constraint that you have. So optimization problems, we have objective functions and the constraint will be decision variables, U. Then now we have nice and beautiful optimization problems, and the next we don't need the modeling. So like I said, the second step is how do you find the optimal solutions? How do you find the optimal solutions? Do you guys have any ideas? Any ideas? S is covariance matrix, n by n, and the symmetric. Because it's a sample covariance matrix. How do you find the optimal solutions? Wow, I'm pretty sure this if for you guys, if that's the first time that you see or you see these kind of things, it's extremely difficult to think about. How to find the solutions for this kind of optimization problems. But there's some brilliant guys say S is symmetric matrix and we can do eigenanalysis, okay, like that. I would say U vectors. And we know that these are eigenvector and eigenvalue. We can find, always we can find. So let's see, we can always find. And let's do, you transpose it. And lambda is scalar, so you transpose U. And what is this? We know we have this kind of same as lambda. So we can write it down, maximize U lambda. That's it. So from this kind of, this is not intuitive. This is not intuitive. But if this one is turns out that same as given S, compute eigenvalues, say conduct eigenanalysis, so then you're gonna find eigenvalues and eigenvectors at the same time and list all the eigenvalues. And the problem is here we want to find the maximize that one, then pick the largest eigenvalue. And the optimal solution is that corresponding eigenvectors, that's you. That's you. I personally, like, when I saw this, the like solutions, how to find the optimal solution, first time it was like, wow, it's brilliant, right? So I hope that most of for you guys kind of have that kind of like emotional like happiness, whatever. Okay, so go back to here is a pick the largest eigenvalues of the sample covariance matrix S, and the corresponding eigenvectors, that's U. That's principal component. That's a principal component. Same as that's the direction of highest variance in the data. Good. So like I said, maximize the variance and minimize the sum of what is that? Minimize sum of squares. I'm gonna show you. I'm done with this. What I'm going to do, what I'm about to do is that I will say that the first and second are identical or equivalent. Let's see. Suppose we have like data set here, and we know that we can find it from eigenanalysis. And suppose that one is the end. I'm gonna make projections, right? And I guess this one is length. We know that this is the length, and since this is the factors and the direction is that u, and u is the unit factors, and x is the x. And here I will say the direction is, this is the e factor for each data point. For each data point. Okay, and I want to compute the length of them, or strength or distance or whatever. And we know that, let me see, this is 90 degree, and we can compute that one. Okay, let me show you that one. So this one is, the length of that is x transpose u, and the length is like x. So the length of this guy is length of square minus, let's say squared, like that. And again, it's think about transpose u, then u transpose x, x transpose u squared, and now we are here. This is the how we compute this, the magnitude of errors for single data point. We have to repeat for entire data set. So that's what we're gonna do. So just to take the mean of it. So we take the summations. And what is this? What is this? Again, it's S. Sample covariance matrix. S. Okay, what is this? The distance. Sum of the distance from the origin in the original coordinate. So let's see, this guy is sum of, or since we divide this, mean of distance from origin to the entire data sets in the original coordinate. It's a constant because data is going to be given. This is constant. And what is this? This is S. We want to minimize that. And since this is constant, doesn't matter when it comes to optimization problems. And we want to minimize that we have minus on it. That means we have to maximize this guy. We have to maximize this guy. Bingo. Minimize this guy is same as maximize the variance. So I think everything is super clear right now. And I prove that. Right, that's, I guess, pretty much all the things that we need for PCA. And okay, so now we're done with the PCA. So now we found unit vectors. And for dimension method is, the thing is that we're starting from like two-dimensional space and we found U, but let's generalize them. Suppose we have the original data set is n-dimensional space. I want to do dimension reductions down to k, of course, like, of course. Then what you need to do is that from S, the sample covariance matrix, compute the eigenvalues and sort them out from the largest to smallest and pick the top K. That's gonna be the new coordinates, top Ks. Okay, then for single data points, make projections onto each vector, each vectors. Then we're gonna have K. This is gonna be new coordinates in new dimension reduction axis or coordinates. We can write it that way, same as in vector form. Okay. So this one is n-dimensional space. This is k-dimensional space. And how do you do the dimension reductions? All the information that we have in the matrix of U. The matrix U consists of top kth eigenvectors of sample covariance matrix. That's it. That's all you need to do for PCA. That's it. Okay. And okay, see, I guess the data is with projection onto unit vector U. So okay, this is don't here in two-dimensional space. And this is the data set in the original data set. And you make projections of U of 1. And this is going to be the dimension reductions, the data set. So basically what we did is from 2 to down to 1. And now after that, probably like regressions, classifications, whatever what you want to do, you can do following with this, right? Pictorial summary of PCA. Pictorial summary. The first step is you have to shift it to make zero mean. And you have to find, from here you have to compute the sample covariance matrix. Out of that, you have to find the eigenvectors. And you make projections. projected one, right? And PCA visualizations again, and you don't have to, the only thing is, okay, so for S, you're gonna compute lambda of 1 and lambda of 2, things like that. Here, since it's two-dimensional space, you're gonna have two eigenvalues. And I'm gonna skip all the details, but remember, like in ellipse, we have like the kind of related to the length of axis, like that. So that means principal component 1, principal component 2. So the magnitude of eigenvalues gonna give us how much information that we're gonna lose when you do dimensional reductions. How much information that you're gonna keep when you do dimensional reductions. Okay, so the magnitude of eigenvalues are related to how much information that you're going to keep, how much information that you're going to lose. And geometric or pictorial meaning is that this is related to like this. Okay, here, I mean, I have to spend more time to explain it, but again, I'm not going to go in details, but it's okay. The eigenvalues indicate the variance along the eigenvectors respectively. So the larger eigenvalues, the more dominant features, or they have more information inside along that axis. Okay, probably I would say it's good to know. So we're done with the PCA, which is good. And let's take let's see. It looks like you might think it's linear regressions and PCA is the same, or is it different, or at least it looks similar. The biggest difference is that linear regressions minimize these guys. X is input and Y is X. I want to predict Y hat. I mean, here is another optimization problems, but objective is that minimize, probably I would say sum over squared. But PCA, again, is same, it's minimizing. Minimize sum over square of what? This. It's different, right? So here we make projections onto U of one axis. And on the other hand, for linear regressions, we make projections on actually along the y-axis. Okay, I hope you guys have clear understanding of, I mean, you already know the linear regressions, PCA, but I hope you guys to understand what make them different, what's the difference these two. And how you write a Python programs. And suppose we generated this kind of data set. And we compute sample mean, I mean the sample covariance matrix, I'm sorry. And again, we have to do eigenanalysis for S. And we have to sort it out. And since it's two-dimensional space problem, this is lambda of 1 and this is lambda of 2. And this corresponding eigenvectors. and we have to make unit. So this, I mean, this is I would say U1 vector, U2 vectors. And this is how we got a plot. This is principal component. And we're gonna make projections. And I made a histogram. And if this is the histogram of errors, then we go the information that we're going to lose. And another thing is that it's widely spread. It's very narrow. That's what we intended for. Basically, for PCA, what we did, we find U of 1 that maximize this and minimize that guy at the same time. Okay. And again, actually we implement it, but we don't need. I mean, this is, I mean, here is really important. If you are able to write a programming on PCA like this, that means you have 100% of understanding of PCA. You're done. Okay. But later on, once we're done with that, like use sklearn dot decompositions and PCA, and that's it. That's it. That's all we need, all you need. And what kind of new dimension reduction coordinates or data points? PCA transformation. That's it. That's it. Get done. All right. Okay, we have only 2 minutes left. We do have some really nice examples or to see what's the benefit that we're going to have. But I think it's the right time to stop here. So let me summarize what we did today. So we did unsupervised learning. We started with the unsupervised learnings. We done with the clusterings last time. So today is we did dimension reductions, and there are many algorithms under the dimension reductions. But again, the most famous and the most, I would say, important is principal component analysis. So that's why I focus on the PCA, and I give you the motivations and the concepts or the insights, and actually I defined the principal component, which is, it turns out that it's eigenvectors, you know, corresponding the largest eigenvalues. When you do eigenanalysis, then we can do dimension reductions. Okay, and I showed you how to program, how to program in Python. Okay, that's all the materials that I have for today. And next time I'm going to continue with the PCA related to examples, which I believe that is very, very nice and it's really cool, right? And I will stop